he said, my name's Stephen Tate, and my advisor for this work is Dr. Stephen Liu at Colorado School of Mines. We've been working on developing laser weldability diagrams for 21 chrome, 6 nickel, 9 manganese stainless steel. So first, a little background on 2169 and also a brief history on austenitic stainless steel solidification cracking. The procedure, the weldability testing that we use to develop this work, some sigma jig testing, and then finally two different sets of results we'll look at. First, the effect of sulfur and phosphorus on cracking with primary austenite solidification, and then the second set, the weldability diagram development to tie impurity content and alloy composition to crack susceptibility, and finally conclusions. So, background on solidification cracking, figured out way back for 300 series stainless steels, have some residual ferrite content and greatly reduce the crack susceptibility. And then finally, Sudolo and Chiampa tied critical chrome over nickel equivalent to solidification mode. So at low chrome over nickel equivalents, you have primary austenite solidification, where your cracking is dependent on impurity content, with cracking at higher impurity levels, which are typically shown as phosphorus plus sulfur. And then at higher chrome over nickel equivalents, here for arc welding of 300 series stainless steels greater than about 1.5, you get primary ferrite solidification and no crack susceptibility, or greatly reduced crack susceptibility. Then as high energy density welding became more prevalent, it was observed there's a shift in solidification mode due to increased undercooling at high travel speeds and the high solidification rates you get at high travel speeds. So with that, there were some different weldability diagrams developed for laser welding. This one in particular is for pulse laser welding, and we see the critical chrome over nickel equivalent shift from about 1.5 to 1.6 to 1.7 due to the increase in solidification rate. And these are both pretty well characterized and well used for 300 series stainless steels, but for some of the specialty stainless steels, we don't really know how well they apply. So the motivation for this work, or the material of interest for this work, is 21 chrome, 6 nickel, 9 manganese, austenitic stainless steel, nitrogen strengthened, nominally about 1/4 weight% of nitrogen. And it's known that the weldability issue of hot cracking is there with primary primary austenite solidification. In the past, it's been dealt with material specifications with reduced sulfur and phosphorus contents. The high cost associated with these type material specifications, as well as the fact that there's composition within these ranges that could be crack susceptible, are both the motivation for this work. And then again, in general, there's an unknown applicability of the weldability diagrams generated for the 300 series stainless steels to these materials. So the weldability testing we used is all sigma jig testing with IPG fiber laser power source. Here's a sigma jig fixture here, fixed jaw, our sample in the middle, and then our moving jaw. The moving jaw is preloaded with a stack of Belvo washers and put a known preloaded tensile stress on the sample. In this case, all testing was done at 45 KSI. And then put an autogenous weld across the sample. And then examine the surface for cracks as well as the transverse cross sections to look for subsurface cracking. So an as-tested sigma jig sample looks like this. This scale is actually in inches, and then the other units are in millimeters here. And so if you look at surface cracking, you typically see the centerline solidification cracks if you do observe surface cracking. But some alloys would show only subsurface cracking. So again, large centerline and sometimes non-centerline cracks subsurface. So the three sections that were taken to look at the subsurface cracking are indicated in these faces here. They're always at the end of the weld where your highest tensile stresses are generated. It's been shown that sometimes at the initial portion of the weld, you typically have compressive stresses actually on the solidifying weld pool. So the first set of results is the effect of minor alloying elements, specifically looking at sulfur and phosphorus levels with primary austenite solidification. There's literature for both 300 series stainless steels as well as high manganese carbon steels that show as we increase phosphorus levels, so this is phosphorus or sulfur, and then total crack length using Varistrength testing, for high phosphorus levels we see a much larger increase in crack length, whereas sulfur get a relatively small increase in crack susceptibility as the content increases. So that was done with experimental laboratory heats of 2169, so all starting from one initial composition and then varying sulfur and phosphorus independently. The compositions or the levels of phosphorus and levels of sulfur are shown here. The numbers in the table just indicate heat number or alloy designation, so they're insignificant. But basically our red alloys show cracking and our black alloys are no cracking. And unfortunately we didn't have anything lower than 0.02 phosphorus as a starting alloy. So we can't look at really low phosphorus levels to see the influence. But even at 0.02 phosphorus, we don't see cracking as we increase sulfur until about 0.05 weight percent sulfur. Whereas with phosphorus, with very low sulfur contents, we see cracking at about 0.036 weight percent. So a much larger influence on cracking from the phosphorus compared to the sulfur. Qualitatively, we also see some differences in crack severity. Alloy 47 here, high phosphorus and somewhat sulfur, larger cracks, whereas our high sulfur alloys are much finer cracks observed for those alloys. And some of the high sulfur alloys like 46 and 50 showed continuous centerline cracks like we're on the title slide. So doing some analysis on the sulfur and phosphorus levels, the reason these alloys were here was to provide a 3x3 factorial matrices to do a factorial regression and see if there are any interaction effects. So looking at phosphorus as a term, sulfur as a term, and then P times S interaction, we see if we evaluate number of cracks, we see phosphorus being significant, sulfur possibly not significant, and then phosphorus times sulfur much less significant. And then looking at number of sections with cracks for a given alloy, we see both phosphorus and sulfur are likely significant, and then P times S is insignificant. For the P values, we're looking for a critical value of less than 0.05. So there's no or little interaction effects for the sulfur and phosphorus. So knowing that there's no interaction effects, we then went and looked at all the heats and just did a general regression on all the heats to try to back out some coefficients for phosphorus and sulfur. So looking at the model for number of cracks, we see 150 times P plus 30 times S roughly. So if we normalize that to a coefficient of 1 for phosphorus, we get a coefficient of sulfur for about 0.21. And then number of sections with cracks, so 220, 215 times P plus 30 times S again. So a coefficient of about 0.15 for S with a coefficient of 1 for phosphorus. So kind of generalizing these and not getting too specific, we chose a coefficient of 0.2 for sulfur to include on the weldability diagram. Looking at why the sulfur and phosphorus behave differently, influencing the cracking behavior, we did some thermocalc shell simulations to look at composition of phosphorus and sulfur in the liquid at high fraction of solid. So with 3 different compositions, low phosphorus, low sulfur, high phosphorus, low sulfur, and then low phos, high sulfur, essentially our min and max points. So with our min sulfur, min phos level, we see enrichment to about 1 weight percent phosphorus in the liquid at high fraction of solid. And we see some enrichment in the sulfur, but not near to the degree that we see with the phosphorus. And then as we increase the phosphorus level, the phosphorus in the final liquid to solidify jumps significantly like we'd expect, and the sulfur remains the same or decreases slightly. However, the interesting one is at high sulfur levels with low phos, we see similar levels of phosphorus enrichment as the minimum impurity content composition, but the sulfur doesn't increase significantly in the final liquid to solidify. And that's due to the manganese sulfides being formed starting at about a 0.4 fraction of solid. So this is just temperature versus fraction of solid with our different phases to form. And again, this is primary austenite solidification, so we go to liquid plus FCC, and then liquid to FCC plus manganese sulfides. Looking at phosphorus by itself for this min phos high sulfur alloy, the third alloy in the table, we, as we'd expect with a typical shell simulation for a partition coefficient less than 1, we just see continuous enrichment in phosphorus of the liquid. However, looking at sulfur as a function of fraction of solid, we started our initial alloy composition and enrich in the liquid until those manganese sulfides begin forming, and actually reduce the sulfur content in the liquid below the nominal alloy composition with the formation of those manganese sulfides. we'd like to be able to look at the films on the crack surface and see what they're rich in, sulfur, phosphorus. We do see some films in the cracks. However, with EDS and the small film size that we observe, trying several different setups, we've been unable to identify any sulfur or phosphorus in the cracks, or in the EDS spectra at least. The silicon level that there is shown is typical of the nominal content of the alloy, so it doesn't look to be enriched in sulfur or silicon any, excuse me. Again, based off the thermocalc shallow simulation as well as some other literature, we expect the sulfur to be tied up as discrete manganese sulfides and the phosphide-rich films to be on the boundaries. However, we can't quite show it with EDS. Looking at the dendritic fracture surface of a solidification crack, we again see these films, but even with the larger volume of film here, the EDS wasn't able to pick it up, likely an effect of the too large of an interaction volume with the material. Then going to the second set of results, trying to develop a laser weldability diagram and tie alloy composition and impurity content to cracking for the 2169 alloys. So we did this with basically 3 different types of material, or kind of 3 subsets, 14 heats, commercial heats of 2169, 7 other commercial heats of similar alloys, so similar nitronic alloys, as well as some other specialty high nitrogen, high manganese alloys, just to see where they fit in, and then 20 experimental heats of 2169. And that 20 includes the alloys looked at in the sulfur and phosphorus variation. Again, we did this for 3 different travel speeds, so we'll look at 50 inches per minute, and then 100 inches per minute, and then 200 inches per minute, so we could capture the shift in critical chrome over nickel equivalent for primary ferrite solidification with those solidification rates. So the chrome over nickel equivalent here are plotted in SP coefficients, which were developed just for the nitronic alloys. And then the impurity contents are plotted as P plus 0.2 times S, that coefficient we determined in the P plus S variation work. Filled symbols indicate cracking, unfilled, no crack. So at chrome over nickel equivalents below about 1.5, we see almost entirely primary austenitic solidification, and then cracking in most of the alloys with greater than 0.02 P plus S, or P plus 0.2 times S, so impurity content. And then a little bit of slope to our vertical crack, no crack line, because we do observe some alloys with similar chrome over nickel equivalents, but we have primary ferrite here, but primary austenite at higher impurity contents. So don't know if impurity content could be influencing solidification mode slightly as well. The one point to the right out here that's an outlier was excluded from the crack, no crack line because it's not a 2169 alloy. That was actually a nitronic 60, high 3 to 4 weight % silicon in that alloy, and kind of showed some different behavior. Going forward to 100 inches per minute, looking at the shift, we see the chrome over nickel equivalent for our vertical line shift from about 1.5 to about 1.7. Our alloys in this region now show a mix of primary austenite as well as some dual mode, so primary ferrite and primary austenite both observed together. And similarly, even the alloys that show no cracking from about 1.5 to 1.7, we see a mix of primary ferrite, primary austenite, as well as some dual solidification mode alloys. And then going on to 200 inches per minute, our highest travel speed and highest solidification rates. The crack, no crack line hasn't changed any from 100 inches per minute. Still see pretty similar behavior there, except for again an outlier that was excluded because it's not a 2169 alloy. That's a 18 manganese, 2 nickel, 12 manganese, 18 chrome, 2 nickel, 12 manganese Carpenter alloy. Again, just excluded because the focus of this work was 2169. The main shift we see from 100 to 200 inches per minute is in the transition region. We've shifted to almost entirely primary austenite solidification. Kind of a clearer demarcation between primary austenite and primary ferrite at our 1.7 chrome over nickel equivalent. On the weldability diagram, it's a binary crack, no crack representation, but we see a wide range of crack severity in the samples. So anything from full-length centerline section cracks on every cross-section we take to alloys showing minor centerline cracking in one section of the 3 transverse cross-sections taken. So we looked at crack length for all the different alloys and quantified that. So looking at number of cracks versus travel speed, we see an increasing number of cracks as we increase travel speed, particularly at 200 inches per minute. However, the total crack length didn't really change, and the reason for that is as our number of cracks increased, our average crack length significantly decreased at the higher travel speeds. We shifted away from the large centerline cracks to larger numbers of small non-centerline cracks. So looking at total crack length as a function of travel speed, it's much more a function of chemical composition than travel speed. Our experimental 2169 alloys with high impurity contents show pretty consistent cracking, as we'd expect with the high impurity levels there. Some of the other non-2169 alloys, or other nitronic alloys that show cracking, again, kind of pretty similar total crack lengths between the different travel speeds, and a little bit lower than our high impurity alloys. And then some of the other experimental heats, the orange here, show, again, consistent cracking at a range of travel speeds and more related to impurity content than travel speed. Interestingly, out of all the 14 2169 commercial heats, only one of them exhibited cracking behavior. We had one alloy that shifted to primary austenite at 100 and 200 inches per minute and showed cracking there. But even some of the other commercial alloys that showed primary austenite solidification had no cracking at those, or no cracking was observed. Comparing 2169 to some of the other alloys, as far as total crack length, for a given impurity level, about 0.02 or a little above 0.02. With nitronic 50, we see large centerline cracks, 4,000 microns total crack length, whereas 2169 at those impurity levels, we see less than 1,000 microns. So in general, the 2169 seems to be quite a bit more crack resistant than some of the other nitronic alloys. And finally, conclusions. Again, phosphorus shows a larger influence on solidification crack susceptibility for the chemical compositions tested here. The weldability diagram to predict the crack susceptibility has been developed for laser welding at multiple travel speeds. We see a shift in critical chrome over nickel equivalent from 1.5 to about 1.7 as the travel speed ranges from 50 to 200 inches per minute. And 2169 shows higher resistance to solidification cracking than some of the other high nitrogen, high manganese alloys. Acknowledgements, we'd like to thank Los Alamos National Laboratory for funding this work. And with that, thank you for your time. Any questions?